Let's talk about numerical differentiation. If we have a term function, then it's not necessary to do numerics, because a derivative can always be built using algebraics, and using computer algebra system you can do that very easily. That's the first thing I want to say, because the next chapter will be integration, and when doing integrating, which is the antiderivative, if you do that, then often it's not possible at all to do that algebraic. So if you want to derive sine of x squared, it's very easy, but if you want to integrate sine of x squared, this is not very easy, and often it's impossible to find an antiderivative. But this is not the topic of that video, but it's the topic of the next video. So let's talk about numerical differentiation. So what is the derivative? Maybe or hopefully you remember the following definition. You have a function f of x, and now you want to find the derivative at some point x0, and this derivative is given by this limit. You take a difference of function values and divide by the distance of the evaluation points, which is h, and then take the limit. Let's illustrate what we do here. We want to find the slope of the tangent, and what do we do here? We can choose an h, and then we can evaluate at x0. We can evaluate at x0 plus h, and then we take the slope of that straight line. We take the slope of the secant, and if h tends to 0, then this limit is exactly the derivative of x at the position x0. But if we do numerics, we can't do this limit. So if following that definition, one idea is very, very easy to have. It's the straightforward idea. So choose some h and then evaluate that expression, and then you have an approximation of the slope. Let's illustrate that with an example. And let's use the function sine of x. In this case, it's not necessary to do numerical differentiation because we know the derivative is cosine of x, and so we can evaluate. So no numeric is necessary for that example, but I'm choosing that example because then we can check everything what we do. So it's only a field of training studying that sine function, okay? So there is a function and there is a point where we are interested in the slope. Let's say this point is 1.2. And now we choose some h which we deem to be appropriate. So maybe we choose h to be 0.0001. Okay, this is some small h. You can choose another one also, but let's choose that one. And now f prime at 1.2 is approximately, following that idea, sine of x0 plus h, 1.2001, minus f of x0, so sine of 1.2, and divide that by h. What means in this case multiply by 10,000. And if you do that using electronic help, be careful that your calculator uses the radian and not the degree system, and then you get what is the correct value. In this case we can easily check what is the correct value. Cosine of x evaluate at 1.2, and then we get, and we see we get a good approximation. It's wrong here in the 5th digit after the decimal point, but the first 4 digits after the decimal point are correct if we apply that. So let's check what happens if we choose another age. Let's choose age to be that, 7 zeros and then a 1. This is 10 to the minus 8. And then doing that, sine of 1.20001 minus sine point 1.2 dividing by, and if we do that, and then we get 0.3623. So we are very, very good. We are better than we have been here. So choosing a small h seems to be a good idea. So let's use an even smaller h. And then we get 0.36637. So this value became not better, but it became worse. So now only the first 2 digits are correct and the third one is incorrect. How is that possible? Mathematically, this does not make any sense. But where are we? We are in the field of numerics. How do I do this calculation? I subtract 2 values which are very close together, and if you subtract 2 values which are very close together, it's almost never a good idea if doing numerics with floating point numbers. So it's no surprise that using a very small h, this is not a good idea. Being in practice, it's not so easy to decide what is a small h and what is a too small h. So in this situation, we learn that this h is too small and this h is a very good one. Being in practice, we can't know which h is really the best one. This is a problem and there is no easy answer to that problem. Okay, this was our first example. Let's do a second example. And we get 6.2002 and then a bunch of zeros, 12757. If you do the calculation by hand, you will learn that the correct answer is 6.2. So we are okay in the first 3 digits after the decimal point, but the 4th digit after the decimal point is not correct. Okay, we will come back to that example later. So if you have this idea, you may ask, why do we use the forward differential quotient? We can also use the backward differential quotient. I want to show you. Instead of using that slope, we can also use that slope. What do you think? Which is the better one, this slope or that slope? The natural answer is it doesn't matter. Both slopes are more or less the same. No, they are not the same, but the quality of the idea is the same. So what is the next step? We have this slope and we have this slope, and so we can take the mean value of these 2 slopes. This might be a good idea. So we can say f prime of x0 is the mean value. Okay, so let's do the analysis of that. Forward slope is f of x0 plus h minus f of x0 divided by h. The backward slope is f of x0 minus, and the mean value is add them and divide that by 2. So what do we have to do? The common denominator is h, so we can add here. We have f minus f of x0 plus f of x0. This cancels, and then divide that by h and divide that by 2, and so we get this one. Interesting is that the value of that point doesn't matter at all. We take that slope to be the slope at that point. And so this is this slope. Okay, this was the idea, and let's have an example. And let's reuse that example. x0 plus h minus sine of x2 divided by h, which is, and what do we get using electronic help? We get, and the correct value is, and that shows that we are much better as we have been before. Before we were correct up to the 4th digit after the decimal point. Now we are correct till 1, 2, 3, 4, 5, 6, 7, 8 digits. Double the number of digits are correct now compared with this. Is that an effect of this special example? The natural feeling being a mathematician is no, because this is a better idea. Both values are to be taken, and then taking the mean value must be a better idea. But let's have a second example, and let's reuse this example. Then we take f of 2.3001 minus f of 2.2999 divided by 0.0001, and then we get, and then 22854. And so we are much closer to the correct value than we have been before. And if you analyze that example in detail, it will turn out that if you perform that difference without any rounding errors coming from using floating point numbers, then this value will be completely correct. So let's write that down. I did that analysis in my script I want to show you. And here I start this analysis. Let's take a polynomial of degree 2, not the special one we had in our example, but any polynomial of degree 2. Then let's analyze this expression, and we get the answer 2 times ax plus b, which is the correct derivative, and then we have the error a times h. And using this improved formula, we get the exact value 2a times x plus b without any deviation. This is the correct derivative. And it's not hard to do that analysis. You only have to expand some terms like that one, and then you see immediately that this formula is exact for polynomials of order 2. That's very fascinating. Why is it so fascinating? That means if you have a parabola like that and you are interested in that slope, you can use h also to be 1000. Then you evaluate 1000 to the right, 1000 to the left, and then taking that slope is the correct value for that. Not in that example, but if you do it correct with a correct parabola and correct distance 1000, then it's completely correct. That's really fascinating. So we get a much better value using that formula, at least for polynomials of degree 2. But this means that we are correct to order 2 using that formula, and we are only correct to order 1 for linear functions if we use that expression, and so it's 100% clear that this is the better choice. Okay, so we have an idea, and we have an improved idea, and maybe we can stop that video, but we can have also one more idea. Maybe this one is much better. Let's check. If we have these 3 points, we can also do the following. We can find a parabola, a polynomial of degree 2, interpolating these 3 points. Then we will get something like that. And then we can derive this polynomial and evaluate this polynomial at that point. And then we get also an estimate for the derivative at x0. So this is an easy idea, but if we want to really do that, we have to really do that. So let's start, but let's make things not too complicated. Let's say x0 is 0, let's say h is 1, and so we have these 3 points, and it's very easy to generalize from this configuration to arbitrarily x0 and arbitrarily h. Okay, these are the 3 values, arbitrarily chosen values, and now let's do the analysis. We will find a function of degree 2, which is a times x squared plus b times x plus c, fitting to these points. And now we can evaluate at -1, then the result should be y minus 1. Evaluating at -1 is a times 1 minus b. X is -1 in the moment, -1 squared is a, -1 is that minus, plus c. Let's evaluate this expression at 0, then we get c. And let's evaluate at 1, then we should get y1, and evaluating at 1 we get a plus b plus c. So immediately we get c is y0, and so we have a minus b plus y0 is to be y minus 1, and a plus b is to be y plus 1. So this is not y minus 1, but y index minus 1. Okay, having that, we can reformulate. Let's bring that to the other side. A minus b is, and a plus b is. Okay, now we can add these two equations, and then we get 2a is that plus that, so y minus 1 minus, and again minus, minus 2 times y0 plus y1. And we can also subtract these two equations, that equation minus that equation, then we get 2b. That minus that is a y1, that minus that is, this cancels, so minus 0 minus 1. And so if we divide by 2 we get, and if we divide by 2 we get, and so we found our function interpolating these 3 points. Now we did step 1, let's derive. So we get 2 times this times x plus this times 1 plus nothing. And now let's evaluate at point 0. Here 0 times something is nothing, and we get, or we can write, and what do we get in our picture? 0. This is this slope. This is that slope of that line, and that means we did not get anything new. We had a new idea, but what we got is the same as we had here. And so we can better understand that. And so we did the analysis that this formula is exact for polynomials of order 2. So we now understood why, if there were no rounding errors doing that subtraction, this value should be 6.2, finish, nothing more, no digits 22854. But what can we do now, having this idea in mind? We can generalize that to using more than 3 points. We can maybe use 5 points. So we can find a polynomial of degree 4, interpolating these 5 points, then derive that polynomial, then evaluate at x0. And if we do that, then we can redo this analysis. This will take a lot more space on paper, so I don't want to really do that now in this video. But I did that, and then I found out the following formula. F prime of x0 is, you will find the formula, evaluate the function at this point, and you will get, then evaluate at that point, take that value 8 times, then skip that value, it's not interesting at all, plus 8 times that value, and minus 1 times that value, and divide that by 12 times h. And so we got a new formula. This formula will be exact for polynomials up to degree 4, and so it's clear that this formula is most times the better one, so you can use also that formula. Let's have a small example. We don't have a lot of space left. Let's have these 5 values, and then we get prime at this point, this value 2.0 minus 8 times 2.2. This value is skipped, then plus 8 times, and then minus that value, and divide that by 12 times. Step width is 0.01, so divided by 0.12, and then you will get the value 32.5. And maybe it will help to do that example also with MATLAB in the following way. Let's use the values. Then let's find the polynomial of order 4. There's a command which is called polyfit. We talked about that in the last video. So let's fit to these points with a polynomial of degree 4, and then we get some coefficients. Then let's find the derivative of these polynomials. We can do that by using the command polyder. And then let's evaluate that polynomial at the point 0.51, and we get 32.5. So this example showed if we apply the formula, it gives exactly the same result as doing that way. But be aware, these calculations take a lot more CPU time than our calculation using our formula. And now one last aspect. If we have a sample function coming from a series of measurements, maybe every millisecond one measure is to be taken, then we don't have a term function which we can evaluate wherever we want. So we have the following situation. Maybe we measure the position of at a discrete set of time values, so 1000 samples in 1 second. And if we are interested in the velocity at some point, then we are not in the situation that we can choose h whichever we want. In this case, you have a very natural h, and that is the distance of 2 adjacent points. So we can use that formula. But in this example, maybe you have a real-time system and you are interested in the velocity at that specific time, and you don't have that value. This value is in the future, and you have to make a decision how to steer the parameters of your car at that specific point of time, and then you can't use that formula. So then you have to take that slope. And it's not possible to use these improved formulas, these improved techniques, then unfortunately you have to do that like we said here. And on top, if you have a sample function and you want to use either that idea or that idea, then being at the first point and being at the last point, you can't use our improved ideas, and then you have to use that slope. Okay, that was the video about the derivative.